In this problem, we want to find all solutions of 2 sine of 3x equal to negative square root of 2. So ultimately, we want to isolate x all by itself on one side. So let's start by getting the trig function all by itself on one side. So let's divide both sides by 2. So we have sine of 3x equal to negative square root of 2 over 2. And we would like to get that x all by itself, so we need to get it out of the sign. So let's hit both sides with the inverse sign. So we have the arc sine of the sine of 3x all equal to the arc sine of negative square root of 2 over 2. And the nice thing about inverses is they undo each other. And so on the left-hand side, we're just left with 3x. And on the right-hand side, we still have the arc sine of negative square root of 2 over 2. Now, if we were trying to find the principal solution, we would grab a hold of this arc sine and compute the exact value of it, and then solve for x, and we'd have a unique solution. But notice in this problem, we are not satisfied with just one solution. We want to find all solutions. And because of the periodicity of sine, we know there's going to be infinitely many here. So the idea is to first find all solutions in one period of sine. We know the period of sine is 2 pi. So we're going to start by finding all theta in one period, 0 to 2 pi. Notice that it's 2 pi because the period of sine is 2 pi. So we're going to find all theta in this interval such that sine of theta is equal to negative square root of 2 over 2. Once we have all solutions in this one interval that is over the entire period of sine, we simply use the wrapping function to get to all other solutions. So let me show you how to do that. We look at the unit circle. I think drawing the picture is always helpful. And we remember that sine corresponds to points on the unit circle as the y-coordinate. And notice that our value of sine is negative. And so we're going to be looking for angles in the third and fourth quadrant because those are the only points on the unit circle that have a negative y-coordinate. So let's draw in the terminal side of all angles in this yellow that have a y-coordinate of negative square root of 2 over 2. So one would be this point right here on the unit circle. And another would be this point on the unit circle. And a quick check will say that these are the only two. That value right here is negative square root of 2 over 2. So now let's write down the corresponding angles. Well, of course, this has a reference angle of pi over 4. And so the entire angle would be 5 pi over 4, just pi over 4 plus pi. And how about this one right here? For this terminal side here, the corresponding angle in blue would go all the way around like this, and we can calculate that that's 7 pi over 4. So there are precisely 2 theta in this interval that make this equation true. What are they? Sine of 5 pi over 4 and 7 pi over 4, and those both live in 0 to 2 pi. But remember, we're not satisfied with just one or two or a couple solutions. We want every solution. And so now let's write down all values of theta that make this equation true. So using the wrapping function, we know that if we start at 5 pi over 4 and go around the circle counterclockwise one time, that would be adding 2 pi to the angle value. Well, we have an angle that has the same terminal side, and hence the sine of this new angle is negative square root of 2 over 2. But we could go around the circle again, and again, and again. It doesn't matter how many times we go around the circle, so we say let's let it go k times. So for any integer k you choose, this theta is going to be a solution of this equation right here. So you choose k equal to 700 million. You have an angle such that when you jam it into sine, it spits out negative square root of 2 over 2. This also works for negative k, though that we would just be going clockwise around the unit circle. So there we've listed infinitely many values of theta that make sine of theta equal to negative square root of 2 over 2. But we also have this value right here, so let's do the same thing. So, or our theta could equal 7 pi over 4, again, plus 2 pi k, where k is an integer, any integer. your favorite integer, plug it in, and you'll produce a value of theta that solves this thing here. I'm being a little bit redundant here, but it's just very important we understand how this k lets us get all infinitely many solutions. One other thing I'd like to point out is notice that this 2 pi in front of the k, it's no accident that is the 2 pi from the interval and the 2 pi that is the period of the sine function. What's in front of the k is always the period of the trig function in question. Finally, we need to relate this to the original equation we were solving. See, so far we have found all solutions to sine of theta equal to negative square root of 2 over 2, but that's not what we wanted. We wanted sine of 3x. So notice all we have to do is take theta equal to 3x and then plug it in and we'll have our solutions. So this is exactly what we do. So here we take this theta and we plug in our 3x. That's equal to 5 pi over 4 plus 2 pi k, or 3x equal to 7 pi over 4 plus 2 pi k, and we now just solve for x. So solving for x in the first one, we divide both sides by 3, so we'll get x equal to 5 pi over 12, I'm just distributing the 1/3 in, plus 2 pi over 3k, or x equal to, again, divide by 3, so 7 pi over 12 plus 2 pi over 3k. K could be any integer. And so right here in this box, we have now listed every possible solution of the original equation. And since there's infinitely many integers, we've listed infinitely many solutions. I encourage you to plug in a few k's, get some actual values, plug them into sine, and verify that they do satisfy the original equation.